Good morning, ladies and gentlemen. Can we just give 2 to 3 minutes for those who are still trying to join with an acceptance of about 185 people? Just a bit of patience, please. Good morning to everyone once again. I think we should start now. My name is Kennedy Safadi, and I'm the Insurance Projects Manager for FPASA. Uh, I am responsible for all the projects that comes through to FPASA via our insurance partner, which is SAIA. The purpose of this webinar is to outline the dangers, the pros, and the cons that lie with lithium-ion batteries. And because our members, corporate and individual, have direct access to us, we have decided to invite external parties to participate in this and give an insight from their end. I would like to introduce the facilitator of this webinar, which will be Marius Ateberi, who is the CEO of FPASA. Marius.
Thank you very much, Kennedy. Good morning from my side also to everybody. It is great to see such a wonderful turnout, and we are looking forward to our two presenters sharing with us today. Just before I introduce the first speaker, can I ask if there are any questions, if you don't mind posting them in the Q&A side, in the chat areas. We will try and collate some of those. Time is a little bit tight to cover the subject. I think a lot of you would have sat in on quite a few of these over the time. So we will try and answer a few questions today. But if we don't get to answering your question, we will put something together, a newsletter or something where we will try and address some of the other questions. So without wasting a lot of time, let me go ahead and introduce our first speaker, Mr. Ruben Babia. He is a postgraduate in industrial physics, busy with a master's in applied science, with a specific focus on storage test bed, energy storage test bed, around lithium-ion batteries and the like. So we welcome him. I'm going to hand over to you, please, Ruben. Stop sharing the screen on this side, and please go ahead, share the screen from your side, and please go ahead. Can I just make sure that, Ruben, you are with us? All right, everybody, sorry for the slight quiet time there. Let me just follow up with our organizing committee, whether we've got Ruben, and that he is actually unmuted to be able to do this. Kennedy, can you check and verify with Ruben?
Yeah, I'm very fine with it, sir.
Right. So while we're just sorting out that little hurdle at the beginning, if you'll allow, I'm also going to do some introductions around the next speaker, Mr. Danny Joubert, so that as we're trying to get things resolved around Ruben, we don't waste too much time with the next set of introductions. So Danny is a veteran of the KwaZulu-Natal Fire Department, also worked in Johannesburg and Benoni, and Danny has progressed into the fire investigation arena and fire engineering since 2002. He has been very active in that arena, and from 2012, his focus was on the fire investigation elements. So let me quickly go back to Kennedy and check if we are having some trouble with
No, no,
Ruben's.
I have sorted out his mic. He should be able to come on now.
Oh, fantastic. There we go. So
Good
let me
morning.
hand over to Ruben. Oh, good. Welcome.
Yeah, thank you. I was experiencing some little bit of technical issues this side. My mic is unmuted, but I still can't share from my side. I can't share my screen.
All right. Can I quickly, Neo, I think you're also on the call with us. You need to make the two gentlemen presenters and not just attendees. And I think that should activate their capacity to share their screen as well. Otherwise, I'm going to ask that you email us your presentation post-haste, then we'll run it from our side.
It looks like you're still sharing, Marius.
Yeah, but that doesn't block him from sharing.
It is.
No, it's not. Actually, he stopped sharing, but still my share button is still off.
All right, Ruben, please try it now. Sorry for the slight delay, everybody.
Okay, yes. Yeah, can anybody see my screen?
Yes, thank you. Please go ahead.
Okay, thank you very much. Is it visible?
Yes, thank you.
Okay.
Understanding lithium ion, we can see that.
Okay, thank you very much. Thank you very much for the introduction. Yeah, my name is Tabang, and as is introduced before, I work with the CSIR, and I'm mostly focused in lithium-ion battery testing, also in the upcoming other battery devices technologies. So I'm just going to give you an overview of what the lithium battery is and what components that make up the lithium-ion battery, and also explain the concept of thermal runaway, which is the main issue of the lithium-ion fires. Okay. Just to take you through, just to get started with the main basic component of the lithium ion fire, which is the lithium element. Lithium element is just a chemical element with the atomic number of 3. And can you see my cursor moving around? No? No. Let's continue. Yeah, it's a lithium. It's an element that has an atomic number of 3, and it's part of the alkali metals in the periodic table. And one of the physical properties and chemical properties is that the lithium element, it's just is soft and silvery white metal, and you can easily cut it with actually your knife. So it's not that hard. And then it highly reacts with water and air. And then upon the reactions, it gives off hydrogen gas and lithium hydroxide. And this is a very less dense metal, which means it floats in water. And this lithium element, when it burns, it actually gives off some urine smelling like smell. Okay, there we go. So now, just to give you an overview of the reaction of the lithium, when lithium reacts with water, It's actually, it floats in water. And when you drop it in water, it floats. That's the first thing that you will notice about the reaction. And it reacts to give off some bubbles. And those bubbles are actually bubbles of hydrogen gas, which is a flammable gas. And then if you heat that gas, you will see what happens. Actually, I have two videos here to demonstrate the reaction. So you have lithium and reacting with water in the first video. And you see, if you can put your lithium in water, it actually reacts violently with it, producing hydrogen bubbles. And those, if you can catch that hydrogen and you light it up or you expose it to heat, it will actually explode. Yeah, which is one of the main factor that plays a role in a lithium-ion battery fires. So with the test tube there, they demonstrated the collection of that hydrogen gas and they expose it to heat, and yeah, it reacts with water. And on the second video, we show the lithium element being melted. And as it melts, it reacts with oxygen and nitrogen. And you see how violent the fire is. It actually burns and melts glass. So you see, if you can see this, it's actually lithium reacting with nitrogen and oxygen in air, giving off a lithium nitrate and lithium dioxide. So these two reactions are the main reactions that lithium, as an element, not as a compound or as a mixture, but as an element, it reacts violently with these substances. Just to take you through the cell structure of a lithium battery, from the name of the battery itself, is a lithium-ion battery, which means the lithium ions are the main components of this system. So if you look at the structure of the lithium-ion cell, it's made up of a cathode material and the anode material. The cathode material is actually coated on top of aluminum foil, and the anode material is coated on top of copper foil. And in the cathode, this is where you're going to find most of your lithium ions. And in the middle here, you have an electrolyte. Electrolyte is just a liquid substance that allows ions to migrate from one side to another. So depending on whether you are charging or discharging the battery, and the movement of the lithium ions also changes. And in the middle here, you will see that there is a separator. And that separator is just actually stands between the anode and the cathode material and avoid them from touching each other. Because if they touch each other, that's where internal short circuiting will occur, which is one of the reasons also that that causes lithium fires. So how these materials are being manufactured? So if you see on your cathode material, you actually have a slurry. So the slurry is just a lithium metal oxide. So this is not a lithium as an element alone. It's a lithium mixed with other elements. And normally it's lithium metal oxide. They coat it on top of the aluminum foil. So this will be your cathode side. So this current collector is an aluminum foil, and this substance here is a cathode material, which is what is shown here. So one of the, just to list few examples of the cathode material of the lithium-ion batteries, you have lithium cobalt oxide, lithium manganese oxide, nickel manganese cobalt oxide, and then you have lithium iron phosphate. This is one of the most famous or popular used subchemistry of the lithium-ion battery. This is normally used in your household for storage of the for the storage of the solar energy. And you have lithium nickel cobalt aluminum oxide, and you also have lithium titanate oxide. I have a very special video that is attached that I'm going to show you with regards to the lithium titanate oxide. Lithium titanate oxide is a very special lithium ion battery. It's robust and it's actually deemed in the literature, it's actually deemed to be the safest lithium ion battery. But the issue with it is that it has low energy density and also low operating voltage. So of course, research is going on in that looks into enhancing the energy density of the lithium ion batteries and also reducing their fire hazards, and thus by increasing their safety. So the cathode side is where actually you will find your lithium ions. This is where most of the lithium ions are. And then the anode material also is just the graphite that is coated on the copper foil. So it's actually manufactured the same way as the cathode is manufactured, just that the slurry, this black material here, is different from the anode and the cathode side. So on the anode side is mostly made from the graphite. So if you don't know the graphite is just actually a carbon material. If you think of your pencil, that needle, that black needle there, it's your graphite. So that's one of the material that is being used on the anode side of the battery. Okay, the battery is not only made of these things, but these two electrodes. So these are called electrodes. You have a cathode electrode and anode electrode. These electrodes are actually sandwiched together. So they are put together, and then because lithium itself has a potential voltage. So if you put them together, it's actually not a desired outcome. So what happens is they normally put a separator in the middle. For them to be able to sandwich these electrodes, they put a separator in the middle. Separator is nothing else but just a plastic-like material, which avoids the movement of electrons within the insides of the battery cell system. Okay, so but this separator is specialized in such a way that it can only allow the lithium atom and the lithium ions to pass through it. Okay, and then this separator is actually submerged in an electrolyte. Electrolyte, as I mentioned earlier, is a liquid that allows the movement of the lithium ions on inside the battery, the cell system. And just to mention, an electrolyte also contains of the substances or the elements also within it that are flammable. So if the battery catches fire for some reason, electrolyte also plays a role in contribution to the fire because it contains elements that are also flammable. Okay. Just to describe the charging and the discharging of the battery. So as I mentioned earlier, the cathode side is where your the cathode electrode is where your lithium ion are more populated, and on the anode side you have less of those. So if you have a lot of ions here and less ions here, it creates a potential difference between the current collectors. And in such a way that if you take a wire and connect it, or you short circuit the battery, the electrons will actually flow spontaneously. Okay. So just to describe the charging and the discharging of this, during the charging, the lithium ions move from the cathode side to the anode side. And as you can see that the separator is in between here, avoiding the electrons from moving inside the system. The electrons, they will only travel in the external circuit. Okay, so here is like your charger is actually separating the lithium. It's actually separating the electron from the lithium atom, and then that electron will actually flow in external circuit, and your lithium ion will propagate through the electrolyte, pass through the separator to the other side. This is the charging process. And then when your battery is full, it's actually telling you that the lithium ion species on the cathode side have been depleted and they actually concentrated on the anode side. So in the anode side, when you're discharging the battery, you actually separating the electrons and the lithium on the anode side, and the electrons will travel on the external circuit, and the lithium ions will actually travel within the electrolytes through the separator to the cathode side. And this electron actually passes through the resistor. This can be anything that you want to power up. Maybe it can be your radio, your load. So hence, the energy of this electron will be dissipated onto your load. And that's if this occurs over and over and over, the lithium ion species on the anode side, they will deplete. Hence, you will end up having your battery being depleted. That's why you need to recharge your battery again. So this is called a cycle. Charging and discharging of the battery is called a cycle. And each and every battery has a specific number of cycles. And you can convert those cycles in the number of years if you will to. But normally you will have a battery that has a 50,000 cycle or even 100,000 cycles. That means you can charge and discharge the battery that number of amounts of cycles. And also the life cycle of the battery depends on how you use it. If you use it more repeatedly and at higher C rates, then you're going to degrade the material. It's either you're going to degrade the cathode material and the anode material. Hence, your battery will be degrading over time. And I think most of us would have experienced this. If you have your phone and you actually abuse it, it will get to a point whereby when you charge it, it will take probably the whole night to charge, but immediately when you remove it from the charger, within before 10 o'clock in the morning, it's already at 5%. So that's actually the degraded battery, and its material has been compromised. So just to give you the types of the cells. So we have cylindrical cells and the pouch cells, prismatic cells, and the coin cells. The cylindrical cells, it's actually just these two cathodes that are sandwiched together with an electrolyte, also with a separator, and they actually roll them around to form this cylindrical shape. And then these, you will mostly find them in, if you can look at the Tesla electric vehicle battery packs, they are made of the cylindrical cells. So this is a picture that shows the cylindrical packs that are connected together to form a battery pack. So you will also find this on your remote controllers and the other devices that needs power. In the pouch cells, the pouch cell is actually a very soft. It's when you touch it, it's actually soft. And it's also made of this sandwiched cathode electrode and anode electrode that are sandwiched on top of each other. So they're actually packed on top of each other to increase the density, the energy output of the cell. And these, you will normally find them in your phones and also in your laptops and the other battery systems. This is a prismatic cell. It's just it's like a brick, and these you'll normally find them in your battery modules that you normally use in your solar systems at home, and also you will also find them in grid scale battery systems. The coin cells are mostly normally known to be found in calculators and also your watches. Okay, so I'm just going to explain the assembly of this. So one cell, lithium ion cell, is normally gives a voltage of about 3 to 3.5 volts. So if you have a load that requires that amount of voltage, then you can actually use a cell alone. That's why even your battery just uses one cell alone. But if you use these batteries for the application that require higher voltages, you can actually pack these cells together to form a module. So one cell, when you connect when you connect individual cells in series or in parallel, they make up a battery module. And these modules, when you connect them in parallel or in series, they actually make up a pack. So this is a battery module. And inside of it, you will actually find the cells connected together. And this module can be connected together to form a grid scale battery system. Yeah. So yeah, to mention about the battery system, what makes a battery a pack system and a battery grid scale battery system, it's actually a BMS. So even your phone and the cars, they have a BMS. A BMS is just nothing else but electronic system. It's called a battery management system. It's just an electronic system that manages and protects the battery from being abused. So think about if when you are using your phone, and it's approaching, you're depleting the battery of your phone. There is a system inside your battery, inside your phone, that will tell you that your phone is now at 15%. It needs to be recharged. That's actually the working of the battery of the BMS. Also, when one cell is overheating inside the battery system, the BMS will actually monitor the underperforming cell and will actually protect it by shutting down the whole battery system. There's another concern about the balancing. Balancing is actually when you have a couple of cells connected together and one cell is underperforming, the BMS will actually shut down all the other cells to fix the cell that is underperforming. Then after that, when the cell is recovered, the whole battery system will come back together to life. Okay, this is a battery management system is normally used for safety and efficiency of the battery and lifespan. It elongates the lifespan of the battery. The thumb rule of the battery is that you're not supposed to discharge your battery to 0% of depth of discharge. And the BMS is responsible for ensuring that the battery is not abused to that level. Okay, that is a basic background of the lithium-ion batteries. So I'm just going to touch on the thermal runaway concept. What is a thermal runaway? Thermal runaway is actually a dangerous and uncontrolled increase in temperature within a battery cell. It's a process in which when one cell catches fire, this cascades to other cells and the whole battery pack will catch fire. Okay, so you have a couple of reasons why would a cell catch fire, which is a cell failure. One of the cell failures, you're looking into short circuit of the cell. As I explained earlier, just to go back quickly on that. So if your separator has been compromised or have been destroyed, now that means electrons can pass from the cathode side to the anode side. Hence, this will cause short circuit. And that's one of the reasons why the cell fails. Also, the physical damage. Physical damage can also damage the separator of the cell, causing it to have short circuit inside. The overheating of the cell. So this picture here shows one cell that is overheating due to compromised material of the battery. And as it's heat up, its heat will be passed to the other surrounding cells, and then when the heat of the the temperature of the cell increases, as I mentioned earlier, that the electrolyte is also flammable. When the temperature of the cell increases, the electrolyte can also be a potential fire hazard. Also, the physical damage, when the electrolyte actually spills, it compromises the cell material, hence by having short circuit inside the cell. So this process starts here when you have a cell that is failing, and even the external temperature also. When you have a battery that is operating in higher temperatures and that temperature affects the electrolyte's viscosity, Hence, the electrolyte can be, can catch fire. And in that case, when one cell fails, when one cell catches fire, it also can affect the other surrounding cells, and the whole battery pack can catch fire. This can be caused also by the poor BMS, battery management system. As I mentioned earlier, the battery management system is supposed to protect this cell here. If the temperature of this cell is increasing and the other temperatures, the temperature of the surrounding cells is normal, the BMS is supposed to shut this cell down, hence balancing the temperature of the whole pack. But if the BMS is very poor, then this will be overseen, then the whole battery pack system will be affected. Okay, so just to give you the characteristics of the lithium ion fire, you actually lithium batteries fires can reach very high temperatures of exceeding 1,000 degrees Celsius, and then once, just to put this statement out there, once one lithium cell catches fire, the advice that we have received in the CSIR is just evacuate the environment, because these guys, they catch fire very quickly, and its fire can spread to the other cells very quickly. And then you can also actually identify this by seeing the smoke. So inside the electrolyte has other elements that are flammable. So when it heats up, there is a pressure, gas pressure that is building up inside the gas, and as the pressure inside the cell, and as the pressure increases, that's a potential bursting of a cell. Hence, it will. Hence, you might have other cells that are exploding within your battery cells. And this gas in this picture, as you can see, the gas that is shown here is very toxic. It has carbon monoxide and carbon dioxide, hydrogen fluoride within, and other organic volatile compounds. And if you have this kind of a gas within a closed room, you won't even survive for about even 15 seconds is enough. You won't even survive. You can also identify the lithium fire by the reddish color. This is due to the compounds that are actually compounds and elements that are actually within the battery itself. So the process is actually, when the gas builds up inside, the pressure increases, and then you end up having the whole system bursting. Okay. Class D fire extinguisher, which is made for the metal fires, can be used, but we haven't tried any in the CSIR. We haven't tried any of the lithium ion. We haven't tried any fire extinguishers to extinguish a lithium ion fire. Our SHEP department has advised us to procure these fire extinguishers that you see here. These are Lithex specialized in lithium ion fire extinguishers. I'm not an expert in fire extinguishers and the fire investigations, so we gotta say this: we haven't tried these lithium ion fire extinguishers, so we don't know how effective these are. Okay, so by so saying, we once had a workshop in the CSIR where one of our departments in chemical cluster, they were actually showing us one compound. It's a material that they use to extinguish fire, and then that the name of that compound is called a drossel. Yeah. So these researcher took a lithium ion battery and he burned it up. And after he applied that drossel fire, it's actually drossel powder. He applied it on top of that fire, and the fire was extinguished. And also on the other metal fires, it was extinguished. I have no idea how that worked. and I'm not a specialist in that, so I will just mention that and touch on it and leave it as it is. So the potential of the fire, if you managed to extinguish the lithium ion fire, it has the potential of reigniting again due to the heat that is still remaining within the battery pack system. Yeah. So in the next slide, I'm going to show you one of the recent case studies that is just a video. One of the recent case studies that actually happened in China. One of the plants caught fire. The plant, they actually manufacture lithium ion cells in China. And one of the technicians reported that it all started with just a spark on one cell. Then the whole building of the plant was gone and lives were lost. So just sit back and watch this video. Yeah, that's about it. So yeah, the lithium ion fires is really a concern in the energy storage industry, and of course, the lithium is very flammable, and the lithium ion fires actually are very dangerous. And you can just imagine having an electric vehicle on the street or on a road, and that is involved in an accident. You know, accident actually will form part of the physical damage to the cell, and that will potentially actually will lead to a cell failure. And as it leads to the cell failure, the thermal runaway will actually happen. Currently, we are working with the fire lab, and they're actually doing the non-destructive testing of the lithium. I mean, they actually do the destructive testing of the lithium batteries. So when they test the batteries, they actually push the batteries to their limits to see at what point do they fail and at what point they catch fire. And also they study this kind of fires and see actually how they can come up with better ways of fighting these lithium fires. Okay. Yeah, that's just to give you a almost wrap up slide. For the future trends and the research directions, we have other developing technologies of batteries. Those are called solid state batteries. So actually, as I mentioned earlier, that the electrolyte of the battery system is flammable. So the solid state battery actually looks into replacing the electrolyte with the liquid electrolyte with a solid electrolyte. That will actually enhance or will make these battery systems much safer. Okay, and also we're looking into as part of our work in the CSIR, we actually working on advanced battery management system. As you know, battery management system is there to protect and to prevent fires of the lithium-ion batteries. So currently, the BMSs that are being used in the battery systems, they are not accurate. Okay? They are not accurate because they estimate the state of charge. They estimate the state of health of the batteries. Most of the parameters that the BMS give off, they are actually estimated parameters. So we are looking into applying AI, artificial intelligence and machine learning into the BMS algorithms so that it can give us, a better and accurate parameters of the battery. A poor battery management system, it will say the state of charge of the battery is 15%, whereas the real state of charge of the battery is 10%. And when you're discharging that beyond that, that's actually, putting your battery under stress, and which can lead into potential fire. So the battery management system is one of the integral systems that also needs to be focused on in regards to research. The thermal management solutions also is one of the research aspects that researchers are looking into. If you can look at this picture, you have a battery packs that are actually embedded into this cooling system. You have tubes around that controls the temperature of the battery systems. If your battery system is heating up, which can lead to potential fire, this system will be triggered to cool the battery down. Okay, and also looking into other electrolyte materials that are much safer and that are non-flammable, and also enhanced battery materials. I put the example of a lithium titanate oxide battery. As I mentioned earlier, LTO battery is one of the battery that is deemed to be safe in the market. And then I have a video here of the lithium titanate oxide battery. I mean, if you're an electrical engineer, you will understand that 0.1 amps of current will actually bring about fatal injuries, or even 1 amp is very, very, very dangerous. It can lead you to, can kill you. In this case, we were running this battery at 900 amps. So we're discharging this battery at 900 amps. You can think how much of that current is. Okay, and currently there is no lithium battery that can withstand this kind of current, because they will actually automatically be shut down by the battery management system. But in this case, we have the LTO battery, and we connected it to our tester, and we were harvesting 900 amps out of this battery. And I want you to sit back and look at what happens here. Other batteries, they would actually catch fire when you are doing that, because their material is not strong enough to withstand this kind of a draw, and also their BMS will be shutting them off. But in here, I want you to look at these cables here that are coming out of the battery. Don't expect anything extraordinary, because we were also flabbergasted, and we were amazed that this battery was performing very well at this test. We expected it to catch fire. You see, as you can see, you have our lithium extinguisher there. We have a cable cutter here, so we were ready for action. If this battery could catch fire, we would put on our respiratory masks and deal with this and take this battery outside and try to fight it. But to show how robust this battery is, I'm just gonna sit back and watch this video. Yeah. Look at these cables here. Yeah, that was it. We drew up 900 amps out of this battery. The cables, they will actually, shaking because of this current is very huge. But the battery was still waiting there, waiting for something extraordinary to happen to itself. And the temperature, just to mention again, the temperature also of the battery was very stable. We expected the temperature to rise very high, but yeah, the temperature was very stable. So this is one of the battery technologies that are proving that researchers are actually out there trying to find safer and even robust battery materials to manufacture. Okay, Thank you very much. That's about it from my side.
Abang, thank you so very much. Please don't disappear. I saw a few questions come in the question area, and I'm going to field them to get your opinion on it, and potentially we might be able to add one or two comments around that as well. So Courtney has started off earlier asking about some best practices around storage, manufacture, transport of the battery environment. So what I want to check with you is in the testing and everything that is being done, all of the work that you're involved with, is there something that the outcome of what you're doing will help inform us to be able to get those safer installations, safer electric vehicles?
Yeah, thank you very much for the questions. I would say, yeah, our team is working on, we are working with the SABS on actually, coming up with standards for battery testing, even the battery installations and the battery, battery use. And yeah, so this is one of the work that we are actually looking into. One another issue that we have is that with the growing demand of these lithium-ion batteries, international markets, they're actually taking advantage of this, and they end up selling us importing less quality or low quality battery cells, of which they can actually result in potential deaths in South Africa. So one of the regulations or the standards that we are looking into with the SABS is the just to have a protocol of importing these battery cells. They need to be tested and checked if they are of good quality, and they are certified for use in the country. And for the transportation, just to touch on the transportation and the storage of the battery, the lithium-ion batteries. So it is advised that when you're operating with, it's the best practice that when you're operating your battery, you must be cautious of the environment at which your battery is working at. The best battery conditions will be, at ambient temperature. And when you are discharging and charging, you should discharge at a very slow rate. Slow rate, okay, I will explain that later on. But yeah, discharging or performing your battery at optimum conditions actually is a best practice. We have done a study in our lab where we tested the battery at the lower temperatures, also at higher temperatures. Unfortunately, our study was only based on this lithium titanate oxide. So, I mean, as we have seen, this battery is very robust, but we could have done this study with other batteries to see how they perform, right? So, but what we have seen is that as you increase the temperature of your operating environment, your battery performance also increases. You get higher capacity out of it. But at some point, when you're reaching about 45 and beyond, you actually destroying the material of the battery, and the battery degrades over time. Yeah, so the best practice is to operate your battery at around 20 to 35 degrees Celsius at very slow rate. Also in the storage of the environment conditions of the storage of the battery are very important. If you store your battery at higher temperatures, you actually affect the viscosity of the electrolyte, and even the lifetime cycle of the battery will reduce, and that will be a potential a danger or hazard to the user. And the other last to touch on is the transportation of the lithium-ion batteries. Currently, I don't know. Currently, I'm not not that maybe I'm not aware of it, but there is no standard that regulates the transportation of the lithium-ion batteries. But as a best practice, it's not advised to transport lithium-ion batteries at a very higher state of charge. So when your battery is fully charged, it's not recommended that you transport your battery at that. So the recommended state of charge will be between 30% to 40%, not even beyond 60% state of charge.
Thank you very much, Tabang. Just before I go ahead with the next question that I'm going to throw at you, Tabang, unfortunately, I have to inform our delegates that Danny has told us that he's now experienced some problems in terms of his connectivity. We've been trying, and that's part of the reason why I kept or started the Q&A with Tabang. But unfortunately, Danny will not be able to join us for the second part of this. What we will do is we will, from FPASA side, make time with Danny, record his presentation at the very least, and then make that available together with the rest of the material. So, Tabang, two parts. The one I hope is going to be an easier one. A lot of people have been asking for a copy of the presentation. The second part, you demystified very much for us the battery management system that it's from our smallest little cell phone. It's in there all the way up to your large installations that we see around. So the question is about the state of charge. Is there a danger to leave the batteries on charge? And are we not creating a situation that if it just keeps on charging and charging, we will be creating an environment where those faults can occur and the eventual thermal runaway can happen?
Yeah, thank you for that question. Yeah, so if it's not advisable to leave your battery charged unsupervised, but because you have your battery management system, so battery management system will do what? It uses the current, because when you're charging, you're actually feeding current into the battery, right? So it monitors that current that gets into the battery. It monitors the voltage increase of the battery, and it monitors the temperature rise of the battery. If the voltage of the battery reaches the threshold value, or even the temperature increase of the battery reaches the threshold value, even the current that you're feeding into the battery, it reaches a threshold value because you program this BMS. So you say, okay, this battery will not take the current that is more than 50 amps. But if you are feeding 50.1 amps, actually the BMS will cut off, will isolate the battery from whatever activity that is happening from the charging process. So I would say if you have a battery management system that is robust in your battery, then the BMS should protect your battery when you are charging it unsupervised. Because when your voltage increases, the BMS will actually cut off the charging process and protects it from being overcharged. Also, the same thing with the temperature. When the temperature of the battery crosses the over temperature value, then the battery management system will shut it down. So just to give you a short answer, if you have a BMS that is robust enough in the battery, then you can charge your battery unsupervised because your BMS will actually supervise your process. But if you have battery systems that do not have BMS, then it's not advisable to charge your battery unsupervised. Okay.
Okay, thank you very much. Quickly want to point out we had a bit of a question around the transportation, and thank you very much, Pamela. for having picked up that in terms of the Road Traffic Act and the Transportation of Dangerous Goods regulations, these batteries would be seen as dangerous goods, and there is quite a robust set of SABS standards on how those things get transported, what can be transported together, what shouldn't be transported together. Just to add to that, the comment that it is not a good idea to charge those batteries to 100% and then start driving them around.
Yeah.
Let me see, we've got another question here about the regulatory environment. And Tabang, I'm not going to put you in a position to try and answer that. Tuva, thank you for that question. The regulatory environment is, in some instances, very useful, that people can latch onto that and find some information. But the technology is moving faster than the regulator or the standards writers can move. So we are looking at a lot of work that's been going on, and Tabang also mentioned some of the work at the SABS. Mary asked about the best extinguishing agent, and Tabang, I saw on your one slide a comment about potentially being dangerous to use water. So if you could talk a little bit about extinguishing agent around the battery rooms, and I see the question is very much in the mining environment, which might put a bit of a different spin on your ideas around that.
Yeah.
But if you could talk us through that, and the comment about the water is interesting for me.
Okay, so yeah, thank you very much for that question. Yeah, I think I'm not a fire expert, but I'm pretty sure that when you have a fire and you apply water in it, you actually reducing the temperature or cooling the whole process, of which is one of the good things in firefighting, I assume. So with fire, with lithium-ion fire batteries is that, as I showed earlier, that on the video that I showed, when you have lithium element submerged in water, it reacts very violently with water. And as a result, it produces lithium hydroxide, and also it produces hydrogen gas. So the issue is this hydrogen gas, because this hydrogen gas is very flammable. So whenever you expose it to heat, then it catches flames. So I mean, I wouldn't advise on using water. Looking it from this perspective of saying lithium doesn't react very well with water. And as you can think about it, lithium-ion battery is made up of lithium everywhere. Your cathode material has lithium, your anode material has lithium, your electrolyte has lithium species inside. And you also have other lithium ions that are running around when you're charging and discharging. So when you expose these ions to water, they will react very violently, hence producing that hydrogen gas. You see, that hydrogen gas that builds up in a cell and ends up, bursting and exploding the cell. So that when that hydrogen gas is exposed to fire or flames, then yeah, you expect to have lithium-ion fire.
Thank you very much. Tabang, to perhaps add some context to a comment like that, in the fire environment, fire industry, we would teach people that they must not use water on a oil fire, for example. And if you go and look at YouTube, you'll see a lot of videos where in a kitchen environment, the pot with oil catches on fire. The moment you put the water on it, it creates a life-threatening fireball. It's just not the safe thing to do. But from a firefighter's point of view, they would walk into that kitchen with their fire hoses all the way open, and they would just flood that thing, and it would not have the same effect. So there's a bit of a ratio element that one has to keep in mind. And I'm using that example because we have found that worldwide, the fire services would advocate that firefighters flow lots and lots of water, many liters per second, onto lithium ion type fires to overpower it, basically with the cooling. But then when they are done, that element that it will start the reaction inside the cells again and it will reignite, means that they would cool it down, move it into a safe place, and then just wait for it to start catching fire again. So, Miri, your question, I don't think we've got a direct answer for you right now. But what was interesting is some of the last footage that we saw on that battery that did not react. Um, and I know that a lot of the battery manufacturers, I've had discussions with Huawei, for example, they are advocating a safe battery uh, standard worldwide that would have an extinguishing agent built into the battery case, not something that we're going to have to come and apply from the outside. Um, Thank you, Andres. I see your comment and everybody can follow there as well. Um, we then have from Lucas a question around the practice where some insurers are currently asking for the extinguishers. And I'm hoping that some of the discussion here would help us eventually get to that appropriate standard. Uh, a lot of work is going on, but unfortunately, uh, our standard creation and our legislation creation is slower than the importing, the do-it-yourself installer, all of those things happening out there. Um, so the type of lithium ion extinguisher, Lucas, that you see floating around, there is work ongoing at the SABS in order to address that certification element. That's got to do with, is the container appropriate to handle the pressure inside? How far will the extinguishing agent reach when it's expelled from the nozzle? There's several testing elements going on so that we can have a better standard, and eventually the next thing after, if we've certified these extinguishers, can they be maintained afterwards? So there's also a maintenance element. All of that work is ongoing, discussions are ongoing, but one thing that I would want to stress at this point, even if this extinguisher is certified, we must still look at the appropriateness to tell a untrained person at his house or her house, buy this and you will now be safe. Tabang mentioned they've been told evacuate as soon as you can. So we might be serving the safety of the people out there better by saying don't install it in places where you cannot evacuate from easily. Install it in a way that can be ventilated easily. Put in some pre safety elements long before we start wondering what's the best extinguisher, because the extinguisher might work, but my batteries are not sitting out there exposed. They inside a box, locked inside a little room that's not reachable. And by the time I open the door to try and use the extinguisher, I might have more problems than solutions. So we are looking at formalizing the extinguisher environment, but it does not mean that it is the best solution for these types of installations. I see there's quite a few extra bits and pieces. Again, Pamela, thank you very much for sharing that. And excellent also. I see, Pamela, you keeping us very well informed. I appreciate that. I'm just checking the Q&A side to make sure that there aren't any other questions. Can I quickly check, for quite a while now, I've seen James and Dexter's hands are up. If you had questions, I hope you put them in the Q&A or in the chat area. Being a webinar, we are restricted in terms of how we can mute and unmute people. Can I just check with the two gentlemen if you can perhaps do take your hands down or post your questions just before we wrap up. Okay, I see, Reinhard, you've asked a question about size. Yes, this is very definitely a consideration. If we look at the extinguisher, that might be good for my little home-based or the small thing that I've got in the office environment that can be done. I see Marie has provided insight there about, or is that a question? Will the HFC gas work? The context that I can give it to you at this point in time, and I don't know if we've got anybody from there, is your large-scale battery installations that we've been looking at. One of the key elements, and I had some involvement when I worked at Eskom with those installations. One of the key things that we had to look at there is distance separation. So you don't put absolutely all of your batteries in one place. So when the thermal runaway starts, you're going to lose all of them. And you can imagine the scale of the fire would be absolutely enormous. So one of the key things is making smaller bits and pieces with distance as your friend between those things. So that's what we've been looking at in terms of that. But then water, as I tried to explain from a active firefighter point of view, fire trucks arriving and the like, water still remains one of the key first response elements that we can put in that will cool down the fire, but that's then not the end of that actual firefighting, because these things would eventually start heating up. We've seen examples from the US, for example, where they would take a Tesla type vehicle, extinguish the thing with water. Locally, we've got some ideas around covering the vehicle with a tarp. The flames might go out, I'd get control of the fire. Then afterwards, they would take that vehicle and they would dump it into a water tank, and they'd leave it there for days. We're all still learning. So that's a very interesting, fast developing area. And we're also looking at hopefully putting some firefighter safety things together from FPASA to help our firefighters approach these things safely. Question about other webinars. Thank you again, Pamela. I see your support there. Very definitely, we would like to know from you what webinars you'd like to listen to. We have started this with Kennedy, and we are really eager to address the need that's out there. So we will definitely look at those webinars going forward. Then we've got Wanda that asks, is it worth recommending to policyholders? Yeah, I'm just trying to, my messages have jumped. policyholders to install effective firefighting equipment? If so, what do you recommend? So the recommendation starts with, don't install this thing where it's going to threaten your life. Then those extinguishers that we see could be, depending on the type of installation that you do, if your batteries are open enough that you can put that extinguishing agent onto the battery, those extinguishers could be a good solution. The point is that right now, we can't tell you that fire curtains is the perfect solution. We can't tell you that the extinguisher is the perfect solution. These things do have value. They can help in terms of reducing life, or improving life safety, reducing property loss. But it's a little bit early to definitively say this is the best solution. And the one installation differs from the next. So I'm sorry that we can't give you a definitive answer, but hopefully that will help. Thank you for that comment as well, James. Appreciate that. I see we have reached 11:17 on my computer's clock. Again, my apologies for our little challenge with the connectivity from our other presenter, but we will certainly make that available. As I was talking, we might even make that a webinar all on its own. Let's engage with them and see what would work best.
Marius?
Yes.
Yes, thank you. I've been raising my hand. I thought you didn't notice. Huh? Okay, yeah, just
sorry, Taban.
No problem. Just to add on what you actually said, I think we should get to a point where we take on studies to actually figure out on how to deal better with these lithium ion fires. Because there's a comment that I saw in charts that say, why can't we adopt the international standards as a guide regarding that? And the other one, it said we should have a webinar about the tools, mechanisms that can be used to extinguish lithium fires. I think, as you mentioned, that we don't have straight answers to say take water and put it there. It will solve it out. I think if I'm not mistaken, in this meeting, in this call, there are a couple of people who have background in chemistry, who have background in physics and engineering, should collaborate and actually go about making studies on how to deal better with this, looking it from all the perspectives, the policy side, the regulations and standard sides, and the government side, and also the science part of these lithium fires. Just a recommendation that we should collaborate and look into these possible studies.
Thank you very much, Taban. I think a very useful proposal, and we will see how we can formalize a way forward based on that as well. And we will be looking definitely at international best practice, etc. So thank you very much for all the comments and for that very good proposal that you've got there, Taban. I see we still have a nice active communication going on in the chat area, and hopefully we can keep this kind of interaction, sharing of knowledge, etc., going on and having it a live activity. We are looking at ways. I know with Teams, you can always, since this is now out there in the Teams environment, you can come and have a look at the recordings and still, even later, make comments and ask questions. I did see the comment about once we've done Danny's part, we will certainly look at what's the best way forward. I'm more convinced now, having said it, that we will most probably try and arrange a specific hour and a half with them to then do that and also have a question and answer session afterwards. The topic is of utmost importance to the safety of people in South Africa. It is of economic importance in so many ways, and we will certainly keep this alive and move forward, and hopefully we'll not only learn from the international environment, but also take things back. You know, the SABS and the like, we are participants in the ISO standards, and even they are running after the problem. There isn't one place where we can go to and say they have a definitive answer as yet. We will feed this back into the international community as well. Can I check with Kennedy and Thabang? Any closing words before we thank our audience that have been fantastic? You've been with us the whole time and excellent interaction. Any last words from you, Thabang?
Thank you, Marius. Yeah, for the last word, I would say I really appreciate the time to listen to me, and I would really like to, to have this kind of engagements where we get the perspectives of, different stakeholders. I've seen in the comments somebody asked about storing the vehicles that are, that have been in accident. I think he's referring or she is referring to electric vehicles. I would say to understand the perspective of individual stakeholder players. If maybe there is somebody who's selling lithium-ion battery fires in their store, they will actually, share their experience and how they deal with things. And other guys from the chemistry research labs, other guys from fire departments, so that we can engage and understand these processes from, different perspectives. So that when we tackling a lithium fire issue, we know we have background from other, other people who have experienced that. But yeah, just to close up, I'd really thank you for the opportunity of allowing me to come here and share my little bit of knowledge with regards to lithium fires. Thank you, Marius.
Thank you so very much. Kennedy, any last questions or comments rather?
Just a closing remark. I'd like to first thank Thabang. Thank you, Thabang, for participating and enlightening us on lithium-ion batteries. I'd like to thank our audience and everyone who took time to attend to this webinar. And such conversations will continue where we'll get experts from the science field, from the engineering sector, firefighters, legislators and regulators to have a conversation till we get this right as a country, and including regulatory bodies. And in so saying, I'd like to thank everyone. Thank you, Marius.
And Kennedy, thank you also to you for all the organizing and for NEO. And a last word of thanks to Thabang and all our attendees. Really appreciated your time. Have a safe day out there. Goodbye.
Bye, cheers.